Welcome back to the Calculus Fun Room. Today's video, I want to talk to you guys about limits of functions. In particular, what we're going to do is look at limits in an intuitive manner. So, meaning I want to explore what a limit is graphically and numerically. So in our last video, we had introduced the idea of limits by talking about average velocity and then instantaneous velocity. Just kind of a quick visual reminder of what we were doing. We think the equation that we had, and I'll bring up the notes in a minute, I think we had h equals something like 16 minus t squared. And we were talking about that parabola giving me the height of an object. So we dropped an object from a tree, something of that nature, and the height was given as a function of time. So as time progressed, the height of the object was given by this parabola and fell to the ground. So what we were doing was finding the average velocity of that falling object, right? And what we introduced was the idea of finding, velocity or speed being, let's say feet per second. So we talked about that was the slope of a line, right? So that was the change in the height over the change in time. That was what would produce our velocity. So one of the things we did was we picked, let's say, 2 points on the graph, let's say from 1 to 3 seconds, and we called this the slope of the secant line. Right? That's not the best drawing here, but we talked about how, let me exaggerate the shape for a moment. We talked about how the secant line was in essence touching the graph in two places. So I'm going to exaggerate this shape here. Right? So we had the secant line touching the graph in two places, and that gave us an average velocity is what that gave us. Right? So this was average velocity. And so what we talked about was, well, how do we make that velocity become instantaneous? So instead of looking over a time interval, a difference of time, right? So instead of finding the change in heights over the change in time between 2 points that we have here, right? So we talked about letting this point approach this point, right? So taking this time value and bring it back to this time value. And in essence, we were letting these 2 points slide closer and closer. And what that did was that made our time interval much shorter. So instead of having like 3 minus 1 as our difference of time, we would look at 2 minus 1, and then 1.5 minus 1, and 1.1 minus 1. So let's bring up our notes real quick from that conversation, just to remind ourselves of a little more detail what we were talking about there. So here is our height function, right? We're talking about the average velocity being the slope of the secant line. So between any 2 points on that graph, that gave me an average velocity, change in height over change in time. And so we numerically calculated what that would be from 1 to 4 seconds. So we looked from 1 second to 4 seconds and found that. And then we moved that time interval a little closer. So we took 2 seconds to 4 seconds, and we found the slope of that secant line, or that average rate of change. So here was the slope between 1 to 4 seconds. Here was the slope between 2 to 4 seconds here. Then we went from 3 to 4 seconds and found that average velocity. And so again, we found the change in height over the change in time, and we found that average velocity from 3 to 4 seconds. And again, what we were doing in this process is when we went from 1 to 4 seconds visually on my graph, from 1 to 4 seconds, my change in time here was, looks like that was supposed to be 3. I think I had a typo on that work. And then from 2 to 4 seconds, I have a difference of time of 2. And then from 4 to 3 seconds, I have a difference of time of 1. So as we have this point here slide closer to that point, right, our change in time is decreasing. So here's our delta t column, and we can see as the 2 points get closer and closer that delta t gets smaller and smaller, and it's going to 0. So this was the limit process that we were talking about in the prior section. We were letting these 2 points get closer and closer. We were letting the time interval get smaller and smaller. We called that the limit process again, right? So symbolically, what we said was the average rate of change would be given by what you might have called a difference quotient. in a prior course. And then when we let the change in time, the denominator, go to 0, right, that gives us an instantaneous rate of change. So again, in the prior video, we've already discussed a limit process, and what we're going to do in this video is we're going to pull away from the conversation of average velocity and instantaneous velocity. We're going to pull away from the application. We're going to talk a little bit more numerically or graphically, visually, what limits look like in general. Okay, so again, in the prior section we had application where we were looking at average velocity, and we were talking about going to instantaneous velocity and instantaneous rate of change. So we're looking at how the y values change in respect to the x values, right, as the denominator went to 0. So in this video, instead of looking at this specific expression, instead of looking at the change in y over the change in x, let's just talk in general about any expression that sits here where the domain value approaches some number. Right, so in other words, let's suppose, we're considering the limit of any possible expression, an equation, some function, and x is approaching any specific number. And we're going to say that this limit has some value. It has some number L that it approaches. So visually speaking, right, let's say we look at this kind of graph, right, and let's say I'm approaching A in my domain, right? So x is approaching A. So I pick a number over here, and I let x approach A. And visually, again, we're picking a point on this graph, and it is approaching this number here. So let's call that, try and do a dotted line, let's call that the number L. So here's our number A and the domain of our function. And so as x approaches A, the y's on the graph approach the value L. And so that's what this expression is stating for us symbolically. Right? And there's a couple different ways we could write that. We could say as x approaches A, f of x approaches L. Right? But usually how we read that is we say the limit of f of x as x approaches A equals L. Right? That's typically how we would read that expression. Right? Now, again, I don't want to look specifically at what we talked about in the prior video, right, where this was the difference quotient. Let's talk about any general function like we had in this graph, f of x. So as an example, what I want to do, right, let's start with an example specifically, and then we'll look in a more general manner. So as an example, let's suppose we're looking at the expression x minus 1 over x squared minus 1. We want to let x approach 1. So what does this limit equal? All right, now remember, as I showed a minute ago, when we did this in the last video, we did some exploration. We built a table. So I want to take that same approach here. So let's say we are going to pick specific values. So we're going to pick specific values of x, and we're going to plug those in and find the values for the function. So what I want to do is I want to approach 1. So, if I think visually, without graphing this function for a moment, if I'm looking at a number line, right, here's an x-axis, and I'm approaching 1, there's two ways that we can approach 1. We can approach 1 from the left, and we can approach 1 from the right. And what I want to do in this table is let's take both ways of approaching 1. So I'm going to start out here at 0, and then I'm going to do 0.5, and then I'm going to do 0.9, and 0.99, and 0.999. Right? So let's start at 0, then we'll go to 0.5, we'll go to 0.9, go to 0.99, we'll go to 0.999. Now the question is, how close to 1 should I get? Should I go to 0.9999, or should I go to 0.99999? Well, honestly, we'll know when to stop when we see an obvious pattern. So there's no definitive way to approach 1 or how close to get to 1. Right? Now let's go from the other side. Okay. So in other words, I'm going to approach from the right, and I'm going to start at, let's say, at 2, and I'm going to go 1.5, and then 1.1, 1.01, 1.001. So I'm going to approach from the right through those values. And again, how close do I need to get? Well, it really just depends on once I see the pattern and see where the limit is going. And again, I want to stress to you with the limit process, we are never getting to 1. We're getting really, really, really close to 1. That's what the limit process entails. We're never going to let x get to 1. We're going to get infinitely close to 1. And again, just to connect back to our prior conversation, in our prior conversation, we were finding slopes of secant lines, right? So we were evaluating delta y over delta x, right? The change in height over the change in time. And our denominator was getting smaller and smaller. So if we look at this column here, our delta t was going to 0. That's what was happening in this table as we explored numerically. So what I wrote in green down here was, well, what if these 2 points become exactly the same? What if delta t actually equals 0? And change in y over change in x is technically undefined. So when we let the denominator equal 0, we get an undefined value. But we can see as the denominator approaches 0, we were approaching a value of -8 in our table. So that's the same concept that we're going to use here again. We don't want x to equal 1, but we want x to get really, really, really close to 1. And that's our idea of what a limit is. Okay, so I want to be as efficient as possible filling this table in. And so, what I could do, could be really old school, or I could take x equals 0, I could plug this in by hand. And I want to go ahead and use technology to do that for me and make this as efficient as possible. So if I'm using, let's say, a TI calculator, Texas Instruments calculator, probably the easiest way to do this would be in the following manner. I'm going to type this expression into an equation. So I'll bring up my calculator, and I already did that. I hit the y equals key, and I typed in our equation here. And then a couple different ways to do this. I could graph this expression and see what this graph looks like visually. And then I could hit the trace button. So if I pull this down for a moment, I want 0, 0.5, 0.9, 0.99. So I could just trace. I could hit the trace key, and then I could just type 0, hit enter, and it gives me that y value. And I fill that table in. Right? So that would be 1. And then I would type, 0.5 and hit enter, and it traces me there, and I fill that value in the table. And then 0.9, and I fill that value in the table. A little more efficient way to do that would be to go to the table. So if I do second graph and I go to the table, the way the table is typically set up is it auto-fills the x values. So I can change that, and that is in the format option. No, I'm sorry. It is in the table set option. So I'm going to do second window and go to table set. And I can choose where the table starts. I can choose the delta table. But what I'm going to do in this case is change the independent variable to be ask. So when I go back to table, the x's are blank, and I'm going to plug x's in, right? So here I can type 0, hit enter, 0.5, hit enter, 0.9, hit enter, 0.99, hit enter, and then I can continue as far as I need to go, and then it's filling that table in for me, right, as I do that, 0.9999, so on and so forth. So I'm going to cheat. I'm going to take a little screenshot of this and fill that table in for me, right? But obviously what I'm doing here, if I can move away, right? I am filling that table in. Go away. Right? I don't need to see that, right? So I'm filling this table in here. So let me pause for a moment and do that. Okay, so I copied and pasted. I did a little screenshot and put that table here. So there's our table values. And now what I want to do is take the same approach. I want to approach 1 from the right. Right, so again, I'm going to start at 2, 1.5, 1.1, and I'm going to approach 1 from the right. Now I could come back into my table, and I could do that. I could hit 2, I could hit 1.5, so on and so forth. Another way to do this, another tool that I could use is Desmos.com. So if I bring up Desmos.com, and I go into the graphing calculator, I'm going to kind of take the same approach here. There's a slightly different way in which I build a table in Desmos. So in the first equation, I typed my equation. Now, a lot of times I could just hit y equals, and type that equation in, but I chose f of x equals because there's a couple different advantages to that. So what I could do right here in the second line is I could type f at 2, and it'll show me that y value, and I could fill the table in. And then I could just come back and type 1.5. Again, here's that y value, and I could just fill in the table. 1.1, there's that y value, fill in the table. I'm going to take a little bit of a different approach here. Another option here is I hit this little plus sign, and I'm going to add a table. Now what it wants is to plug in specific values, which it'll call a list of x1, y1. What I'm actually doing is I'm going to plug into f of x. So I'm going to click up here, and I'm going to just backspace and call that f of x. And then, actually, let's do this. Let's call it f of x. I'm just going to hit the number 1. So it's going to choose these values in the table, plug them into my function. So if I come down here, hit 2, enter 1.5, enter 1.1, 1.01, 1.001, 1.0001. So it's just plugging in for me quickly, and it's building a table in that manner, right? So I could use a graphing calculator, I could use, a table. What's kind of cool about this process is notice how it plotted all the points on the graph. So as I started at 2, it moved closer and closer to x equals 1. So I'm going to pause the video for a second, take a screenshot of this table. All right, now we do have the tables there, but I also want to look visually for a moment, right? Just so we're connecting the numerical data in the tables to the graphical visual representation. And again, so with Desmos, right, we saw as we approached 1 from the left, right, we started at 2, from the right, we started at 2 and we came in from the right. We can see those points trying to get to a specific y value. Now, if this is y equals 1, it looks like 1/2 is what it's trying to get to. And we can see in the table that's definitely what's occurring. We started at 1/3, 0.4, 0.7, 0.4999999. So as closer and closer and closer we get to 1, we're going to get closer and closer to 0.5 here. I'll bring up my TI calculator. What I did was, I was on the Y screen, I hit graph, and then I went to the zoom and I chose the decimal option, zoom 4, and it kind of zooms into the origin a little bit. And what's kind of neat about the TI is it's trying to show me there's a hole in the graph at x equals 1, right? Obviously, when I plug x equals 1 into the denominator, I get division by 0. So we can see from the graph at x equals 1, we're gonna have a hole on the graph. So as I approach 1 from the right, we're approaching 1/2. And as I approach 1 from the left, we're coming down into 1/2 as well. All right, so I just took a screenshot and put that in our digital notes here as well. So again, as we approach 1 from the left, we can see the graph coming into 1/2. You notice the values are larger than 1/2, and they're coming into 1/2 from above. So we can see values that are larger than 1/2, and we're coming into 1/2 like from above. And then as we approach 1 from the right, notice the y values are smaller than 1/2, and we're coming up into 1/2. So we're smaller than 1/2, we're coming up into 1/2. So our answer here for our limit, we see numerically from the left and from the right, we're approaching 1/2, and we can see visually that as well. All right, so I'm going to write symbolically here that the limit of x minus 1 over x squared minus 1 as x approaches 1 will equal 1/2. Again, I want to stress to you here that we're never getting to x equals 1. We're letting x approach 1. We're getting super, super, super close to 1, but we're never actually getting to 1. That's what the limit process entails for us. Now, one other thing discussed with you here as well, right? How on earth are we getting 1/2 out of this when I plug x equals 1 in, and I get division by 0? And what we could do in this example is a little bit of algebra simplification. If you notice that this expression here of x minus 1 over x squared minus 1, right? The denominator factors. Get x minus 1 times x plus 1, and the x minus 1s are going to, cancel out, if you will, right? So I really have 1 over x plus 1. So instead of plugging x equals 1 into here, we in essence are plugging x equals 1 into here, and we're getting 1/2. However, I want to caution you, right? This isn't always an option. This algebra cleanup is not always an option. There are quite a few function we're going to see in a calculus class where that kind of cleanup doesn't happen. So we're going to need to take different approaches to evaluating the limit than just simplifying and plugging the number in. So there's a couple different ideas that I want to come back and summarize here, okay? And one of them being that we can approach a function from the left, we can approach a function from the right, We can approach a value in the domain from the left, we can approach a value in the domain from the right. So in this case, my domains are x's, right? My outputs are the y values. So what we're looking at in this scenario is as the domain approached 1 from the left, and as the domain approached 1 from the right, we're looking at the y values on this graph. So again, here we're letting the domain values approach 1. We're looking at the outputs, the y values. Right? So when we wrote, where's it at? When we wrote this expression up here, right, these are the outputs of the function and these are the inputs of the function. And that's what we're discussing in a visual manner. As we approach A in the domain, and the point slides on the graph, what are the y values trying to get to? So again, a couple concepts that we've introduced here that I want to come back and let's formalize, let's generalize. And the first thing I want to focus on is the visualization. Now notice in this particular example, we in essence have a hole in the graph. So our limit is existing, right? Our limit has a value of a half, but there's a hole in the graph. Now again, we talked about how that is totally okay. The function does not have to be defined at x equals 1 because we're never getting to 1. We're getting infinitely close to 1. So the limit can exist. It can have a numerical value, in this case 1/2, even though the function's undefined at 1. So let's just talk about a couple other visual representations or graphical where we might see that same type of idea, right? So the example we just saw here is that we might have a graph that has an open hole, let's say. So at A, we're approaching L, right? But we have an open hole. So limit of f of x equals L as x approaches A, but note that, f of A is not defined. Okay. And we also could have a scenario where we have that same type of graph where f at A is not defined on the continuum of the graph, but we have defined f at A at a different value. Right? So, this is L and this is A, but this is something else, right? So maybe L is the number 1/2 like we had, but this is the number 1. So the function could be defined to be 1 when we get to x equals A. But again, the beauty of the limit is we're never getting to x equals A. We're approaching A. So whether the function is defined at that point doesn't matter. It's as we get really, really close, what are the y's trying to get to? And then again, probably the most obvious situation here would be where there is no hole in the graph, right? We just have a continuous graph. So the point is on the graph at L as we approach A, right? So in this case, the limit is approaching L as x approaches A. And in this case, f at A actually equals L. So let me come back over here. Say f at A is defined, but it's not equal to the y value of the limit. So here, the graph is continuous. As we approach the point x equals A, the y values are trying to get to L, and the function's defined at that same point, right? Here the limit is approaching L from the left and the right, but the function is not defined as L, it's some other value. And then here in this scenario, like we saw in our example, the function's not even defined at that point. So visually speaking, in all three of these scenarios, we have the limit equaling a number regardless of what's happening when we actually get to x equals A. All right, now the other thing that we kind of introduced in our example that we looked at is what we call a one-sided limit. So we can see that numerically, right? We talked about when we approached 1 in this example, we could approach 1 from the left, we could approach 1 from the right. Numerically, we saw what that looked like for that specific example. We approached 1 from the left, we saw the y values getting closer to 1/2. We approached x equals 1 from the right, we saw the y values trying to get to 1/2. So we talked visually about what the possible scenarios that might look like, but also that example introduces notationally what we would call a left hand and a right hand limit. So we could have the limit of a function as x approaches a number from the left, and that's how we're going to denote that symbolically, right? So we're going to let x approach a from the left, right? We would call this the left-handed limit. Some textbooks might call that the left-sided limit, right? And then if we're approaching from the right, we could say x approaches a, and we use a little superscript of a plus sign. So that indicates that we're approaching from the right. So again, this is a right-handed limit. So then technically, the original limit that we wrote, when we wrote the limit of f of x as x approaches a, what this really indicates symbolically is that we're approaching from 2 sides. So this is a 2-sided limit. So I have 3 different notations to be able to write symbolically, right, to communicate symbolically what type of limit we're discussing. So a left-handed limit, we put a little superscript of a negative. A right-handed limit, we put a little superscript of a positive. And then when we don't write either one of those, that is understood to be a 2-sided limit. All right, so every textbook has a formal definition of a 2-sided limit. And it usually goes something like this. It usually says that the 2-sided limit of a function will equal a if and only if both of the one-sided limits equal L as well. So the limit from the left would have to also go to L, and the limit from the right would have to have the same value. So this is the formal definition of a 2-sided limit. We say a 2-sided limit exists, right, and equals L if and only if the left-hand and right-hand limits approach that same value. So as we move deeper into this conversation, and in the next video that we're going to look at where we use what we call the limit laws, this is a very important key concept. For us to define the 2-sided limit, we have to investigate each right-handed and left-handed limit in order to conclude that the 2-sided limit does in fact exist. Alright, so I paused the video for a minute just so I could draw this kind of funny looking graph. All right, and I'll kind of let you pause the video for a second for you to be able to draw this graph as well. So now that you've unpaused the video, right, let's take a look at this funny looking graph of some function we call f of x. So we don't have the equation of this function, we only have the graphical representation. And I want to just focus on the idea that we just discussed of one-sided and 2-sided limits. So what I want to do in particular is look at these points where the graph is discontinuous, if you will. So let's take a look at x equals -2. So I want to take a look at all 3 possible limits here. So I want to take a look at the limit of f as we approach -2 from the left. I want to take a limit of the function as we approach 2 from the right. And then I want to discuss the limit of the function when we look at the 2-sided limit. Sorry, those are all supposed to be -2's. Let me fix those real quick. Alright, so I fixed those real quick. We're approaching -2 from the left, we're approaching -2 from the right, and we're approaching -2 from both sides. So when I come over here to the graph and I look at approaching -2 from the left. So again, I'm approaching -2 from the left-hand side. And what I'm really doing is I'm envisioning a point on the graph, and it is approaching -2 on the graph. The inputs of the function are approaching some output the y values. So as I approach negative 2 from the left, the y values are trying to get to positive 2 here. So I'm going to say that left-handed limit equals positive 2, the outputs of the function. Now when I approach negative 2 from the right, again I'm looking at the domain, so I'm approaching negative 2 from the right hand side, and I'm envisioning a point on the graph sliding, and I'm looking at what are the y values trying to approach. So as x approaches negative 2 from the left, the y values are trying to get to positive 2 here. Now, what's the two-sided limit? So we just wrote down a definition of a two-sided limit, and we said the two-sided limit exists if and only if the one-sided limits have the same value. So since the left-hand limit equals 2, the right-hand limit equals 2, then we can conclude that the two-sided limit also equals 2. Now, let's take a look at the other discontinuity here at x equals 1. So have some kind of bad board management here. I apologize for this. So let me change colors, and let's say we're going to look at approaching 1 from the left, we're going to approach 1 from the right, and then we're going to look at the two-sided limit. So let's take a look at approaching 1 from the left of the function, right? What does that equal? We're going to approach 1 from the right. What does that equal? And then we're going to ask, what's the two-sided limit? Let me put a little border here for visually we can see the difference. All right, so if we come back to this graph, and again we're letting 1 approach from the left, we're letting x approach 1 from the left on our graph. So as we approach 1 from the left, if I start a little to the left, I'm down here on my graph. So as I approach 1 from the left, this point on the graph is trying to get to here. And that's an output of negative 1. So as x approaches 1 from the left in the domain of this function, the outputs on the graph are trying to get to negative 1. So there's that left-handed limit. Now the right-handed limit. So as we approach 1 from the right, again if I'm a little to the right, I'm looking at this point on the graph, and it is sliding into here. So as I approach 1 from the right, these y values are trying to get to positive 1 on the graph. So that's a value of positive 1. So when I look at the two-sided limit, what do we say about the two-sided limit? Well, based on the definition, in order for this two-sided limit to exist, the left-hand limit and the right-hand limit have to have the same value. And we can see in this situation that's not occurring. As we approach 1 from the left, we're getting a value of negative 1. As we approach 1 from the right, we're getting a value of positive 1. So what we're going to say about the two-sided limit is we're going to say it does not exist. Right? So shorthand, what you typically see in a textbook is we're going to write D and E. That limit does not exist. Now again, why does this limit not exist? Right? We're going to say since the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. So by definition, the two-sided limit has to exist when the one-sided limits equal the same value. So again, here's a visual representation of that definition. Wanted to draw a graph where we had kind of both scenarios. We had a limit from the left and a limit from the right being the same value. Therefore, the two-sided limit exists there. And then we have a limit from the left and a limit from the right having two different values, and therefore the two-sided limit does not exist. All right, I'm going to take a look at another example with you. In this case, we're going to take a look at a limit which we'll see quite a bit in the near future. We're going to look at the expression sine x over x, and we're going to let x approach 0. Now what I want to do with this example is basically the same thing we did with our very first example. I want to explore numerically, and then I want to explore graphically. Okay, so again, bringing up that last example, before we officially discussed left-handed, right-handed limits and things of that nature, we had explored this expression, this limit, x minus 1 over x squared minus 1. And what we did was we approached one from the left in a table, we approached one from the right in a table, and then we saw graphically what that looked like. Now I pointed out, right, we had a quick conversation, a little note down here, that in this expression we were able to simplify the function, right, the expression, and we could see that the division by 0 that we encountered would cancel out, if you will, right? And temporarily we could plug in x equals 1 into this expression and see that limit of 1/2 that we were getting in the tables. Okay, so in this example, I'm going to take the same approach, right? Let's build a table. Let's explore what we would see with this function. Let's look graphically, right? And then let's note to ourselves that we can algebraically simplify this expression. Right, so again, I don't like my videos to get too long, so I'm going to be a little efficient here. And I'm going to approach 0 from the left and from the right, and I'm going to use tables of data. So, you know, if I'm filling out a table and I'm writing things on paper, what I'm doing is I'm looking at values of x approaching 0, and I'm looking at what happens to sine x over x, right? And, you know, again, if I think numerically on a number line, when we approach 0 from the left, we're going to start at, let's say, -1, -0.5, -0.1, -0.01. So this is how I would approach 0 from the left, right? And again, how close to 0 do I need to get? Just depends on how quickly we see the pattern of the y values here. And then again, I'm going to approach 0 from the right, and I'm going to look at this expression. All right, so again, you know, on a number line, if I'm starting at 1, I'm going to 0.5, 0.1, 0.01. So that's me approaching 0 from the right, numerically speaking. And again, I want to be efficient to complete this table, so I'm going to bring up, you know, my graphing technologies to do that. So again, let's do the sine x over x and the ti first. So hit my y equals button, I'm going to clear this, and I'm going to do sine of x, and then I'm going to divide by x. Now, for those of you that use graphing calculators, it's really important for us to remember that when we graph trig functions, we always graph in radian mode. So I want to make sure that I hit my mode key here, and to make sure that I'm in radian mode, and I can see that I am. Right, so if I'm in degree mode, hit enter to select degree mode. I want to make sure that I select radian mode, because that is how we always deal with our trig functions in a graphical manner. Now, if I go back to the table, I already had it set up as ask, right? So keep in mind what I did is I went to second window to the table set, and I changed auto to ask. Now, these values I don't want, so let me delete those values. So I'm approaching 0 from the left, right? So I'm going -1, -0.5, -0.1, so on and so forth. So I'm going to type -1, -0.5, -0.1, -0.01. And notice we're already see, right, the calculator gets annoyed, if you will, right? It says, I'm going to round for you. If I plug -0.01 into the expression sine x over x, I'm not going to get 1 out of that, or I'm going to get a decimal. And usually what you can do with your calculator is you can hit your arrows and highlight that number, and here's much more decimal accuracy. So because it rounds to 4 decimal places for its display of the value, it is rounding, right? It's rounding from the 4 decimal places, and it's giving you 1. And obviously you can see the y values are approaching 1 pretty quickly. So there's really no need for me to fill out this other value that we wrote on the table. We'll go ahead and type it in, right? But we can see that's what that value would be, right? So this value is 0.999983. This value is 0.99999983, right? So we're getting to 1 very quickly there. Right, and again, just as a review, if I come to Desmos, I'm going to type SIN. I'm going to use parentheses to stress what's inside the sine function. I'm going to hit the division key and put x. Right? So here's my graph of sine x I'm seeing rather quickly. And again, we can see as we approach 0, we're approaching 1 from the left and the right. So my two-sided limit is going to exist here. But let's remind ourselves of how we would do that as a table. So I would bring up table, and I want to change to f of x, because that's how I named my expression. I named my expression f of x. And actually, we want to plug in the values in the table that are the x1 label. So I'm going to approach 0 from the right in this case. So I'm going to go to 1 and 0.5 and 0.1, 0.01, 0.001. Right? So again, we can see Desmos carries a little more decimal accuracy. And again, the cool thing about Desmos is it's plotting those points as I create that. Okay, so taking screenshots, again, right, here's my two values of my tables. I have, as we approach 0 from the left, and our TI. Right, we can see, right, we carry more decimal accuracy, but not in the table. Right? So I have that filling in my table here. Okay, and then from Desmos, right, we took the same approach, and here was us approaching 0 from the right. So again, visually speaking, right, I'm going to bring up the TI real quick, and being in radian mode, when I graph, right, I can see the values approaching 1 here. And when I bring up Desmos, we can see the same thing. I'm going to scroll and zoom, right? We can see we're getting closer and closer to 1 in a visual manner. Okay, so here we see our graph. Now again, as a reminder, right, in this section, our focus is not algebraically evaluating these limits. Our focus is looking at a table of data as we approach the number, closer and closer and closer to the number, and looking visually. We've also talked about what we call a two-sided limit. So we're looking at a left-hand limit and a right-hand limit, right? One-sided limits have to equal each other in order for the two-sided limit to exist. So in this section, we're focusing more conceptually, graphically, numerically, without looking at algebraic techniques. And there's one other concept in this video that I want to discuss with you, and that would be called limits at infinity. Alright, so in this last example, I just wanted to pause the video for a second to draw a graph. I didn't want you to have to watch me to do that. So take a moment, pause the video, and draw that graph for yourself. Alright, now that you have unpaused the video, let's go ahead and talk about limits at infinity. So you'll notice on this graph in red, we have 3 different discontinuities in this case, and those being vertical asymptotes. So we can see at -2, we have a vertical asymptote. At x equals 1, we have a vertical asymptote. And at x equals 3, we have a vertical asymptote. So let's just move chronologically from left to right through our domain of this function. So let's take a look at -2. So let me use green, and let's call this -2 in green. So just like we did in the prior examples, I'm going to take a look at the limit in 3 components, right? So I want to take a look at the limit as x approaches -2 from the left. Let's say this function is called f of x. Let's take a look at f of x as x approaches -2 from the right. Forgot my -2 here. Let me fix that. Approaching -2 from the left, we're approaching -2 from the right, and then we're looking at the two-sided limit as we approach -2. Right, so if I come back over to the graph, I try and animate this concept. So we approach -2 from the left, we're looking at the points on the graph, and where are they going? So as I approach -2 from the left, the points on the graph are getting larger and larger and larger and larger. Right? They're growing without bound. And in essence, in this case, they're going off to positive infinity. So we would say the limit of f of x, as x approaches -2 from the left, the outputs are growing without bound, going off to positive infinity. I want to stop for a second here and talk about our notation. Technically, nothing can ever equal infinity. So the fact that we're saying this limit equals infinity is a little misleading. Now keep in mind what this limit is really saying notationally is I never get to x equals -2, I let x approach -2. It gets infinitely close to -2. So what we're really saying with this notation is that the y values are getting larger and larger and larger. We would say that a little more precisely as they grow without bound in the positive direction. So they're getting larger and larger positively. So again, we're saying this limit equals infinity, but of course nothing ever equals infinity. All right, now if we approach -2 from the right, so if we look at our graph, we approach -2 from the right. Again, my points on my graph are growing without bound in the positive direction. So we're going to say that limit equals positive infinity. And therefore, the two-sided limit would also equal positive infinity, right? So the left-hand limit equals infinity, the right-hand limit equals infinity. Since these one-sided limits are equal, then we say the two-sided limit also exists and approaches infinity. Okay, so just to make a little bit of room on my writing space, my digital paper here, I'm going to pause the video. I'm going to erase what we just wrote. So pause the video for yourself if you haven't finished writing down these notes before I erase them. All right, so now I'm going to use the color gray, and moving chronologically, let's take a look as we approach 1. So I'm going to look at the limit as we approach 1 from the left. I'm going to look at the limit as we approach 1 from the right, and I'm going to look at the two-sided limit. So we're looking at the limit of our function. As we approach 1 from the left, we're looking at the limit of our function as we approach 1 from the right, and we're looking at the two-sided limit. So again, I'm trying to animate this, right, as a point on the graph. So I'm approaching 1 from the left. So as I approach 1 from the left, I'm looking at points on the graph, and I'm looking at where are they trying to go. So in this case, the points are going down towards negative infinity. Now again, the limit can never really equal negative infinity. We're saying the y values are, and I want to say this, that they're growing without bound. They're getting larger and larger in the negative direction. Now, so I realize that's a little bit confusing. Right? If we think of a number line, numbers that are larger than 0 become bigger and bigger and bigger. Numbers that are to the left of 0 are technically getting smaller and smaller and smaller. But what we're going to do in this case is we're going to think in terms of size or absolute value. So as numbers get larger and larger in the positive direction, we're getting to positive infinity, right? They're growing without bound in the positive direction. And as the numbers get smaller and smaller and smaller, what we're going to say is they grow without bound in the negative direction. So in absolute value, they're getting larger, just in the negative direction. So then we see the same type of behavior when we approach 1 from the right. So when we approach 1 from the right, the points on the graph are going down towards negative infinity. And therefore, the two-sided limit will also equal negative infinity. Again, the one-sided limits have the same value, so the two-sided limit exists and has the same value. Now again, I'm going to pause the video to erase, to give myself more space here. So pause the video for yourself so you can finish writing down the notes here. All right, so the last thing I want to look at then is approaching 3 in terms of a limit. So I'm going to pick orange here. I'm going to take a look at the limit as we approach 3 from the left. So we're letting the limit as x approaches 3 from the left. We're looking at what do the function values do. We're looking at the limit of f of x as x approaches 3 from the right. And we're looking at the limit of f of x as x approaches 3 from both sides. So again, visually, I'm going to try to animate this for ourselves. So here's 3. We're approaching 3 from the left. So if I look at points on the graph, as we approach 3 from the left, these points are shooting down to minus infinity. Now, if we look at approaching 3 from the right, again, I'm looking at x equals 3. I'm approaching 3 from the right. I'm envisioning points on the graph and where are they trying to get to? Right? What are the outputs? And those are growing without bound in the positive direction. So we're going off to positive infinity. And then since the left-hand limit and the right-hand limit aren't equal to each other, we're going to say the two-sided limit does not exist. Okay, so this last example I want to look at here, in summary real quick, what we talked about was looking at limits in a more general manner. So instead of looking at a specific example like an average velocity, we were looking at limits of any function. And in particular, we ultimately looked at a two-sided limit. We defined that in terms of the one-sided limits. We looked at some visual examples where we might have a two-sided limit that doesn't exist, at a discontinuity where we possibly have holes in the graph, and then in regards to vertical asymptotes where we have limits going off to infinity or negative infinity. We also talked about how to explore limits numerically in a table and using some technology to make that a little bit more efficient. In the next video, we're going to look even more specifically at limits. We're going to talk about algebraic processes. So instead of exploring in a table or in a graph, we're going to talk about how we could deal with the expressions to be a little more precise in how we evaluate those limits. I look forward to seeing you next time.